We have already started photo-induced electron transfer reactions last time. Photo-induced electron transfer reactions. We have already seen few examples of this. Few more examples, and we have mentioned that this is a donor acceptor in the presence of light. So we have a donor, we have an acceptor in the presence of light. There is an electron transfer from donor to acceptor. Donor becomes radical cation and acceptor becomes radical anion, and then these radical cation and radical anion pairs undergo different reactions. So a large number of reactions have been reported in the literature, and then we will see a few of these examples today. So when we have an alkene, the donors are rich alkenes, electron rich. Several examples of where the electron rich alkenes have act as an electron donor, and the acceptors are dicyano benzene, dicyano naphthalene, dicyano anthracene. So these cyano derivatives of the aromatic hydrocarbons have been can act as a very good electron acceptor. So we'll see an example here. We have an alkene like this, C double bond O, diphenyl 1,1 diphenyl 1,1 diphenyl ethylene, 1,1 diphenyl 1,1 diphenyl ethylene. When it is irradiated in the presence of dicyanoanthracene, there is an electron transfer from in methanol, CH3. So this act as a donor, this act as an acceptor, this is a solvent, and then this is of course light. So there is a under photolytic condition goes to an excited state and then transfers an electron to anthracene, and then we get radical cation and radical anion pair. So we get a pH is an electron transfer. This is radical cation, and dicyanoanthracene becomes radical anion. So this and then this radical. So if we can write just for specifying where the radical and cations are. So we have a, say for example, we have a radical, this is a cation here, is a radical here, and then this can add to another molecules of D, can add to another molecules of the starting 1,1 diphenyl ethylene. So it is going to add from this side so that it can pH, it can add to. So two molecules of diphenyl ethylene are reacting to give a we get a CH2, a positive charge here, diphenyl, and then we have a radical here, the diphenyl, and then there is a this cation is trapped by methanol by adding the lone pair electron on this, and then it is a methanol is added, OCH3, pH, and then you have a radical, and then you have a, sorry, there is one more carbon, pH. Now this this radical can undergo one more electron plus one more electron plus H plus, then becomes then it's going to add H here, pH, OCH3, pH. So this is the a product which is a methanol added product. So we have already seen it earlier also, and now this is an example. This is a nucleophile. These radical cation are trapped by nucleophile. This radical cation, the radical cation which is formed is also when treated with oxygen. So it O2 reacts with oxygen, so it has nicely it has been shown to react this radical add to oxygen to give an intermediate like this, phenyl O phenyl and positive charge. Now this radical. So this plus an electron, it also acts as an electron and then becomes an anion here, and then so it has been found to have a cyclic endoperoxide. So the formation of this endoperoxide very clearly indicate that the radical cations are generated and then it can easily be trapped by oxygen. So this is the evidence for the unit. So this is a very good example of trapping of radical cation by oxygen to generate followed by to give an endoperoxide. Endoperoxide peroxide formation indicates the endoperoxide. Let me just remove this. So let's see another example here. If we have a system, it has also been shown that if we have a dyne like this, in the presence of light, SnCl4 being the electron transfer the agent, there is an electron acceptor, and the CH2Cl2 being the solvent. There is an electron transfer from this dyne to SN4 to generate a radical cation. Radical cation, right, and then this has been found to undergo again it has been found to react with oxygen. It has been trapped. So if we can another example of trapping of this radical cation by oxygen. So if we specify this and write the specific radical right, and then this one going to a radical cation conjugated. A radical here, the positive here. This is again trapped by oxygen. O, right. Then you have a positive charge. Then there is of course, there is a transfer of an electron from donor plus one more electron becomes anion and then it gets cyclic. So again here we have an endoperoxide formation. So you can see the stereochemistry is nicely maintained. The attack is going to be from the front side. So this is endoperoxide. So this is another example of a trapping of existence of a radical cation species, trapping of the radical with the oxygen to generate a proxy radical, the transfer of one more electron to give an anionic species which can couple to give the final product. So another lot of several examples of electron transfer with dicyanoanthracene have also been reported. So this is an example of a 1,4-dicyanonaphthalein, which is an acceptor, plus tetramethylethylene. This is a donor. This is an acceptor. 1,4-dicyanobenzene, tetramethylethylene. In the presence of light, electron transfer takes place from donor to acceptor, generating a radical anion. Radical anion and radical cation species. And if we specify this, just to see the specify the radical anion and radical cation, so we can see the generation of you can see, say for example, you have a radical cation like this, plus it is a, you have to generate a radical anion by one of the double bond. So you have a radical anion here, Cn is a Cn, another Cn here, radical anion. Now this radical anion may, there is a possibility of addition of this donor to the anthracene derivative. So addition of donor to an acceptor has also been reported, and then this becomes so we have a if we can get a system like this, double bond Cn, the Cn here, and this on further undergo loss of a cyanide and then addition of minus H plus. So this goes like this, minus Cn to give a fully aromatic system. So one of the Cn is lost with the addition of, and then this lose minus H plus to give an alkene. So it's one of the one of the H from the methyl group lose to become a double bond. So you can see the addition of first the electron transfer from electron rich alkene to electron deficient dicyanobenzene to generate a radical anion and radical cation pair, donor acceptor pair. And then this donor acceptor pair has been found to addition of the coupling of the radical. So you can see how ethylene is adding to the dicyanoanthracene to get this one of the product. So this type of reactions have also been found. So similar reaction with the has also been reacted with not only anthracene but another thalamide. If you have a system like this, so this carbonyl is acting as an electron acceptor. This acceptor is acting as a donor. In the presence of light, electron transfer takes place. Then we have a of course a donor acceptor pair. Donor acceptor, this is a radical anion plus radical cation, donor acceptor pair. And then if we can specify this, the radical anion on the carbon, of course, obviously the electron is going to add to the carbonyl to generate a radical. So if you can write this in a showing the specifying the radical anion, and of course specifying here also a radical cation. There is a possibility of radical coupling here, so get a product like this. Right, then we have a positive charge here, OH. Of course it will lose O minus. It may lose a proton from it will lose a proton from here and accepted by the OH. So get a double bond here and OH here. So finally it has been found. This is another example of addition of donor acceptor to give a added adduct. So we get OH. So this is another example of similar type where donor acceptor under fertility condition undergo electron transfer to generate radical anion or radical cation. Then there is a radical coupling and followed by a loss of proton shift, H plus H plus minus H plus. From here is proton shift. So this is a really interesting example of both this one where the donor acceptor are adding to get the added product, indicating the photolytic condition under photolytic condition generating electron donor acceptor pair. The another example is the dicyanoanthracene plus so in the presence of light in methanol is an acceptor, this is a donor. In a photolytic condition generate electron hole pair, electron radical anion and radical cation pair. Radical anion, this is an acceptor. After accepting generates a radical anion. After donating proton, after donating electron becomes radical cation. And then if we can write this in a more specific way to see how to see the product addition, so we'll excite one of the double bond to generate radical cation and this one as a radical anion. So as we have seen in the previous slide, so specifying a radical anion here, Cn plus a radical cation here, is a possibility of radical coupling to generate Cn positive charge. This of course comes and becomes Cn minus here. There is a loss of Cn minus, and this we have all, and also addition of methanol is adding. So we'll just see first loss of cyano. We'll just doing stepwise. We can also do in one direction. Then there is a methanol addition may also take place. CH3OH to give OCH3. This is another similar example where the dicyanobenzene is acting as electron acceptor, where under photolytic condition the presence of methanol is added, as well as there is a tetramethylethylene is added to the acceptor with the loss of cyano group minus Cn to give this product. So these are large number of reactions have been done involving photoinduced electron transfer reaction between donor acceptor, which where under photolytic condition donor gives an electron, acceptor accept an electron, generates electron hole pair. The electron hole pair once again not radical cation or radical anion pair may add radical coupling to generate this added product followed by methanol, or loss of a proton to give this. Another intramolecular, if the donor acceptors are present in the same molecule, the intramolecular electron transfer is also reported intramolecular. Intramolecular electron transfer reaction where donor acceptors are in the same molecule. So if you have a system like this, C double bond O N, C double bond O, right? So we have a CH2 and then there is ethylene here. So this in the presence of light containing methanol as a solvent, this is acting as a donor, this is acting as an acceptor. There is an electron transfer from this alkene to carbonyl to generate a radical anion and dianion. So if you can, it goes to electron transfer. So we can write a radical anion on the carbonyl O minus. We have already seen one separate example of this. Now this ethylene part, the donor part, is already in the so you have a radical here, there is a radical here, the positive charge. Now this of course methanol can add as with radical coupling as well as addition of methanol to this to trap this positive to this, and of course to trap this positive charge, as well as the loss of proton from this may be abstracted by OH minus to becomes OH, O minus to become OH. So we have a C double bond O which becomes OH, N, C double bond O. We have a 4-membered ring, 1, 2, 3, 4-membered ring here. 1, 2, there is a methyl group. There's a right. This is a so we have OCH3. So this is a very good example where the construction of a 4-membered ring is observed when the donor acceptor are in the same molecule. This type of systems have been exploited by taking different examples, and we can see in this reaction. Thank you very much. In continuation, we can also see we can see another example of cyanonaphthalene. So we have seen that the cyanobenzene, cyanonaphthalene, cyanoanthracene, cyanophenolphthalein, all these can act as an electron acceptor. Electron transfer reactions. So here the acceptor is cyanonaphthalene. Cn, cyanonaphthalene, plus tetramethylethylene is the electron donor. We have an H nu electron transfer reaction takes place in the presence of methanol. So you have we have a radical cation, a radical anion pair, cyanon Cn minus radical cation pair. Now you can specify this to see the radical addition product. So if you can generate a radical anion and a radical cation, and so we Cn here, a radical anion to across this double bond, plus plus we have a radical cation of this, and there is the addition of coupling of this radical to give, and of course there is a shifting of this negative charge, and Cn negative charge here, there is one H here, this is one H already here, right. So you can see the addition of methanol here, as well as a proton be abstracted by this to give the dihydro. Cn OCH3. So you can see here again a similar type, the donor acceptor added product, the electron donor on transferring electron to this cyanonaphthalene can undergo radical coupling followed by methanol addition. So solvent addition, donor acceptor addition product. So and we see the phenanthrene, cyanophenanthrene has also been used to accept an electron to give a this is cyanophenanthrene plus we have a dicyano the tetramethyl ethylene as a donor. In the presence of light, again you have a methanol, so we can have as usual, you have a donor acceptor radical anion and radical cation pair. Cn radical anion plus radical cation pair. Now we can specify the radical anion, radical cation, just to see the how the ethylene is adding to this cyanophenanthrene, cyanophenanthrene, and then we can see here radical anion. So we have a cyano here, a radical anion plus radical cation, and then the radical coupling followed by methanol addition, CH3OH, CH3OH, plus of course the so we can have plus H plus as well to this anion. So, and it has been found that the product which is formed is a we have a cyano here, is a of course the addition of the ethylene, so OCH3, the two, so you can see the addition is generating a stereo specific product with a specific geometry. So you can see this is So you can see a very nice adduct of ethylene to this tetramethylethylene. Tetramethylethylene, and can add. So you can see this is an example of a donor acceptor reaction under favorable condition in methanol. Electron transfer takes place from tetramethylethylene to the cyanophenanthrene, generating radical cation, radical cation, radical anion pair. The radical coupling of the ethylene to the cyano derivative, and then followed by methanol addition and the H plus to this proton. So these are all, you can see that we have a reaction with cyanophenanthrene, we have reaction with cyanonaphthalene, we have reaction where the donor acceptor are in the same molecule, and the construction of a 4-member ring is really challenging for the construction of this from synthetic organic chemistry is involved, because and similar here also this dicyano benzene, you can see here is phthalic anhydride, phthalimide, and then we have it benzene, and then we have, of course, trapping of radical species by oxygen in this one as well as in this one. Yes, thank you very much.